Today we're looking at Unit 5, Perpendicular Bisectors. We already have done perpendicular bisectors before. We said a perpendicular bisector divides a segment in half at a 90-degree angle. A perpendicular bisector divides a segment in half at a 90-degree angle. Okay? So when I have a segment and I have its midpoint, so it's divided exactly in half. Let's say this is segment AB. The perpendicular bisector is going to go through that segment at its midpoint and intersect it at a 90-degree angle. So it's going to go through. It can be a ray, a line, a segment. It doesn't matter what it is. So it could have two endpoints. That's fine. You could name them C, D. Okay. So I have two segments there. I have segment AB. I have segment CD. Let's say I have my 90-degree angle here. Which one is the perpendicular bisector? AB or CD? CD. It's the one that's doing the cutting. It's like the scissors. So it's not the one that's getting cut in half. It's the one that's doing the cutting in half. So CD, segment CD, is a perpendicular bisector of segment AB. If you don't know, the upside down T means perpendicular. You should write it when you write the upside down T so that you start associating those things together. Okay? Alright, so we are going to use our triangle parts reference guide that we've been working on, where we have found the altitudes, and we know they intersect at the orthocenter. We have found the medians, which we know intersect at the centroid, so orthocenter, right, inside my triangle for an acute, at the right angle for a right triangle, outside the triangle for an obtuse. My centroid is the center of all the centers, and remember we said that this length here from the side is half the length from the vertex, or vice versa. From the vertex is twice as far as the length to the side. Okay. And then we did angle bisectors, and we said when they intersect, it's always inside the triangle, and their intersection is the in-center. It's the center of the circle inside the triangle. So the in-center is equidistant to all the sides. Okay. Now we're going to look at the perpendicular bisector, and we're going to see that they are going to intersect in a circumcenter. Okay? And we'll talk about why it's called that and what that means. So, in order to find my perpendicular bisector, the first thing I have to do is find the midpoint, because it has to go through the midpoint. So I'm going to use my ruler, and I'm going to find the midpoint of a side on my, I'm going to start with acute. Find a midpoint of the sides. I'm going to measure it. I use centimeters because I like my life to be a little easier when I can have it be easy. Life's hard enough. Don't make it harder for yourself. So if this segment is 6 centimeters, then the midpoint's going to be at 3. And we already did this when we did the medians, right? If I wanted to draw in a median, I would just turn my ruler and I would make a straight line that connected to the vertex. But today it has to be perpendicular through that point. So if you look on your desk, you should have a little Post-it note. The reason I gave you Post-it notes is because they're easier to work with than for some of you than is a protractor to measure 90 degrees. Your Post-it note has a perfect little 90-degree angle on the corners of it. So you can just line it up with the side and that point, and then you can see where your 90-degree angle should go, right? So then you can just line your ruler up with that and draw in your perpendicular bisector. Notice I drew it as a ray. You could go both directions. You could draw it as a line. You could stop when you got to the opposite side of the triangle and draw it as a segment. However you want to draw it. I drew it as a ray. So that is a perpendicular bisector. It's going through the midpoint at a 90-degree angle. Okay? We can do that to each side. So I'm going to go to the next side and measure it. This side is about 4.2, so 2.1. And since these were 3 and these are 2.1, they need different size tick marks. And then I'm going to grab my Post-it again and help myself by making that nice little perfect 90-degree angle there, right here. And then I can use my ruler to draw in the perpendicular bisector. Okay, might have. Nope, I got it. So now I can see where the other segment is, but I can't do like I did yesterday where I just connect, because I need to find my starting point, because my starting point has to be the midpoint. So I can't just like use one of these corners that's already built in like I did yesterday for the angle bisector. So I do still have to at least measure and find that midpoint. So when I measure this one, it's about, I would say 6.4, so 3.2-ish. We'll see how well I did. And again, that was 3, that was 2.1, and these are 3.2, so different size tick marks for different lengths. And then I'm going to grab my trusty little Post-it, line it up. And depending on how well you did, they should all intersect in the same spot. Pretty good. And that is called the circumcenter. And we'll talk about why in a minute. So my circumcenter is inside the acute triangle. We're going to see what happens with the right triangle. So far on 2 of them, they've been inside, and then on that very first one, the orthocenter, it was at the right angle. But let's try this one. All right, for my right triangle, if I measure the hypotenuse, the side across from the right angle, that is, how long would you say that is? 7-ish?
7.
Okay, so 3.5? Tick mark, tick mark. All right, I'm going to turn myself upside down. Not myself, but my paper upside down. It would be funny if I turned myself upside down. This side is how long?
6.1.
6.1-ish. So that's going to be just barely past the 3. Before the 3.1. Between the 3 and the 3.1. Oh, I didn't draw in my 90-degree angle. I just did my 2 midpoints. Well, might as well do the last midpoint while I'm here. Last midpoint. This side is almost 3.2. Right about there. Alright, well I didn't draw any of my perpendicular lines, so I'll do that now. I'll just get my trusty little 90-degree angle, line it up, and sketch. $90. I forgot to put my box. And the next one. Line it up. And the last one. Oops, 90 degrees. Degrees. So where did these all intersect at?
On the hypotenuse.
On the hypotenuse. So in my acute triangle, my intersection was inside. On the right triangle, it was on the hypotenuse. Any idea where you think it'll be on the right, on the obtuse triangle? Outside? Do you think it's going to be outside, going outside like it was on the last one where it was down below the obtuse angle? Or do you think somewhere else? Any ideas where you think it'll be?
Above the obtuse angle.
Above the obtuse angle? Think about what happened over here, right? As I went. Here it was inside, and then we got onto the right angle, and then we ended up outside the obtuse angle, right? Here we were inside, and then we were on the hypotenuse, so we're going to actually we should end up outside the hypotenuse. But let's check and make sure. All right, so we're going to find our midpoints using centimeters. Life's hard enough. How long you say the bottom is? 8.1. 8.1? Tick mark. Might as well while I'm here make my 90-degree angle. Turn my paper 3 times. Turn it around. How long was the long side? 10.2, so 5.1. Tick mark. I lost my Post-it. There it is. If after the process your Post-it is still a good Post-it, if you'll leave it on your desk for the next class, that'd be great. If you wrote on it, that's fine. Then just take it with you or throw it away. But if it's still good, we can use it again. Save some trees. 90, I forgot to mark 90 and 90. One more. This side, how long is this side?
3.9.
Yeah, 3.9, almost 4. So almost 2. And my Post-it. Oh, I didn't get that quite close enough. Try it again. Alright. So in the last one, 2 of them intersected, but the third one didn't. But does it really? Remember, perpendicular bisectors, I made them all with rays, but they can be made with lines, rays, or segments. So I could take this ray that I made, and it's really doesn't have to be a ray. It could be, oh, this one's way off. I did not measure this one well at all. They should, in theory, intersect in the same spot. One of those is not a midpoint or not
I didn't get that.
90.
Could you try again?
Talking to you, Siri. Siri thinks we're having a conversation, and we're not. All right. So, when you look at your notes, it says the circumcenter is equidistant from each corner. Okay? So what that means is if you were to measure the distance from this center to the corner, so for example, you know what, I'm going to do it in pencil. Pencil. I got long arms. Okay, I don't really have long arms, but I tried to tell myself I do. If I measure from the center to the corner, it's about 3.2 on this one. And then if I measure from that center to the other corner, look, it's also 3.2. And if I measure from the center to the last corner, it's also 3.2.
Isn't that the same as the angle bisector?
So the angle bisector is not the same to each corner. Look how long it is to this corner. It's 5 centimeters from here to that corner, but then this to this corner is only 1.5, right? So on my angle bisectors, it was the same distance, not to each corner, but to each side, right? And we called that a radius of the circle that touched each side. So think about this one. If I were to think of those 3 segments that are all congruent, if I were to think of those instead of as just congruent segments, but I thought of those as a radius, watch what would happen. If this is a radius, if I close my compass and make this, oh my gosh, this compass is tight. And make the radius of my compass the length of that, oh, that's way too big still. There we go. So my radius is this length there. It keeps moving. Sorry, my compass is being I can't think of a word. A not nice compass. Right. There. What? It's being difficult, yes. Okay, there we go. So there's my radius. Watch what happens as I go around my triangle. You might say if you were Christopher Columbus, as I circumnavigate this triangle. Look what happened. I made a perfect little circle that touched all 3 of the little corners all at the same time. If I come over here and I put myself right on that intersection, it's not going to work on my obtuse triangle because, no, it's because I didn't do a good job drawing it. Because remember, my intersection was a little off. But it should work on this one because they did intersect pretty well. But I can show you 3rd period. I did a better job in 3rd period. I was more in my measuring game 3rd period, I guess. Okay. It's not going to work so well in the last one, but I'll show you 3rd period. Here's 3rd period. I did a better job measuring. You can see the circle there and my intersection. Okay. So the circumcenter is the center of the circle that circumnavigates the triangle. So that's how I remember circumcenter. Circles around the triangle. Your circumcenter circles around the triangle. Your incenter is the circle inside the triangle. Your centroid is the balancing point, and your orthocenter are the ones that come to your height. You're straight down, orthodontist, right? All right, so there are those. It's equidistant from each corner, the center of the circle around the outside. Okay? In an acute triangle, it's always going to be where? Inside. In a right triangle, it's going to be, we can even be more specific, it's going to be the midpoint of the hypotenuse. And in an obtuse triangle, it's going to be outside. Okay. So we've seen this picture before. Let's look at it again. Name a perpendicular bisector in this picture. So it has to be 90 degrees and it has to be bisecting. BG. BG is our perpendicular bisector. And it's drawn for us as a ray, so I'm going to name it as a ray. You could make it a line if you extended it the other side. You could stop it at G and make it a segment. But for us, it's drawn in there as a ray. All right, name an angle bisector.
AD.
AD. because I can see this angle CAE has been divided into CAD and DAE. So segment AD. It's drawn for me as a segment, so I'm going to draw it as, or I'm going to write it as segment AD. It could be a ray, it could be a line. It is a segment for us. My median, which one's a median? BE. It does intersect at the centroid. I don't have a centroid in this picture though because I only have one median drawn, so I need another median to find it. But this one here is my median because it goes to a midpoint from a corner. So it is a segment, and it can only be a segment because it's a distance. It's a measured distance. Okay? And then last but not least, my altitude. Which one's my altitude? CF, because it has that 90-degree angle, and it doesn't bisect the opposite side like a perpendicular bisector does. It just comes from it has to come from a vertex. CF. And it's also going to always be a segment because the altitude is measurable, right? The pilot can tell you what altitude you're flying at because it's measurable. All right. Next. The perpendicular bisectors of the triangle below are drawn, and they intersect at circumcenter P. It's hard to tell where P is, but P is this one here. So since that's my circumcenter, ladies, since that's my circumcenter, that means if this was to scale, it's not, I checked it in third period, and it does not make a perfect circle. But if this was to scale, it would make a circle that would touch each corner exactly perfectly. Something like this. Mine's a little ovally, but it's because it's not to scale. Okay? If AP equals 3x plus 9, AP is 3x plus 9, and CP is 51, CP is 51, find the value of x. What should I do to find the value of x?
3x plus 9.
Yeah, because A and C are the vertices of the triangle, and they're the points on the circle, and the center is here. That means A to P and C to P are radii, that's the plural of radius, of the circle with center P. And therefore are congruent. And if they are congruent, that means they have equal measures. So the measure of one, 3x plus 9, is equal to the measure of the other, 51. What do I do to solve?
Subtract 9.
Oh, yep, that's a 9, not a 1. Subtract 9. X equals 42. Then what? Divide by 3. X equals 14. Point O is the circumcenter of RTS. So that means if this was to scale, then the circle that goes around RTS would hit each corner perfectly. It's not to scale. It's a little smushed. Okay? So then it says segment RO is congruent to. So it wants to know what other segments does it match? Does it have the same measures as? So segment RO from R to O is going to be congruent to what other segment? TO and segment TO and what? SO. From the corners in, those are all the same. That's different from yesterday. Yesterday it was from the sides in. They were all the same. SO. Now on RO, this time it says just the distance from R to O equals. So this time instead of being what is it congruent to, it wants to know what is its actual measure. What is the actual distance from R to O? Which is the same as T to O, which is the same as S to O. 5. These are all 5 units. They all match each other. Okay? Then RT. RT is this whole side. Any ideas? Yeah, I'm going to have to use the idea of a right triangle. Let me find mine. Do I have a yellow pen? That didn't come with yellow. Rude. So if I use, for example, this triangle right here, it's a right triangle. We're always going to have a right triangle if we have perpendicular bisectors drawn in, right? Because we know it had to be perpendicular. When I look at that triangle, if I were to come out and sketch that triangle off to the side, that yellow triangle, where this piece is 5 and this piece is 3, I can find, oops, I shouldn't call that C, I can call it A. Why can't I call that side C? Why couldn't I call this C? C is usually reserved for the hypotenuse, right? So I don't want to confuse myself. So in this one, A, B, C, A squared plus B squared equals C squared. So A squared plus 3 squared equals 5 squared. A squared plus 3 times 3? 9. Equals 5 times 5? 25. What am I going to do next? Subtract 9. Are we lost? Did I go too fast?
No.
Okay. A squared equals 16. How do I get rid of the square? Square root. A equals 4. In algebra 2, we'd say it equals positive and negative 4, but we're talking about a distance here. So 4 is my answer. Now on your test, there were at least 2 problems on the last test you took where a lot of you got halfway to the correct answer. You answered this problem and you said 4, that's the answer, and I see that's letter C, got it, done, moving on. But I didn't answer this question. I found A, which is this much, and this much, because they both have single tick marks, but this was asking me for the whole trip from R all the way to T. How far is that? 8. There was one where it asked you for the side length of a triangle, and some of you found X to be 5, but then you didn't plug it back in and find out actually how long the side was. There was another one, I don't remember what it turned out, but you found the X and you didn't actually plug it back in to get the answer. So you have to make sure you're answering the question that's being asked, right? The last one, R to S, is the same thing. I want to find this whole side, so I'm going to have to use this triangle in here. It's another little right triangle where one side is 1, the hypotenuse is 5, and we don't know the other side. I'm not going to use A this time because I already used A and I don't want to confuse myself in my work. So this time I'm going to call it B, and I'm going to say A squared plus B squared equals C squared. So this time I'm going to do 1 squared plus B squared equals 5 squared. Oops. 1 times 1 is?
1.
5 times 5 is?
25.
25. Oh, come on. So I've got 1 plus b squared equals 25. Take away 1 on both sides. B squared equals 24. How do I get rid of the square?
Square root.
Square root. So b equals the square root of 24, which isn't square rootable. But it would be nice if you simplified it. Do y'all know how to simplify square roots? Do you remember that? So to simplify a square root, you look, is there a perfect square that can divide evenly into that number? Which of these divides into 24? Well, 4, right? 4 times what makes 24?
6.
6. So I could rewrite this as the square root of 4 times 6. Right? That's the same thing. But I can square root 4. When I square root 4, it comes out of the square root and turns into, what is the square root of 4? 2. So b is really 2 square roots of what's left inside? 6. Cool. 2 square roots of 6, but that's just one side. So if I have 2 square root of 6 on one side and then another 2 square root of 6 on the other side, how many total square roots of 6 do I have?
4.
4 square roots of 6. If you get a calculator and make it a decimal, make sure you round to how many places? 3. Alright, last thing for today is called the Perpendicular Bisector Theorem. And this is a test question on your test, which will be the Friday after break. So we have the rest of this week, we have the break, we come back for another week, and then we take a test that Friday. The following week is all review for exam. Okay? Alright, so if a point is on the perpendicular bisector of a segment, it's the same distance from both endpoints. It's equidistant from both endpoints. So here I have a segment that's been bisected at a 90-degree angle. So this is my perpendicular bisector. Okay, it's saying any point you put anywhere on that perpendicular bisector is going to be equidistant to the endpoints of the original segment. So just pick a place, put a point. If you measure from one end to that point, for me, it's where I put it, it's going to be just barely over 5 centimeters. When I measure the distance to the other side, it is also going to be just barely over 5 centimeters. Those two distances are exactly the same. It doesn't matter where I put that point. I could put that point up high like I did. I could put it down low. Oh, what did I do wrong in this picture with my labeling, do you think?
Only 1 tick mark.
Yeah, right? I've already got 1 tick marks. Odds are this is a right triangle. Well, it is a right triangle, which means I know these two can't be the same because it's the hypotenuse. It's got to be longer. So I'm going to change that to 2 tick marks. Alright, so if I put a point here and I measure, that is about 3.5 for me. And then if I come to the other side, guess what? It's also 3.5. 3 tick marks this time because it's different than the other two. No matter where I put that point on that line, it's going to always be equidistant from both endpoints. I could even have put it underneath if I wanted to. I could have put my point down under here and drawn it in, which is just barely over 3.5. So here, notice it is also just barely over 3.5, 3.6-ish. Always equal. Okay? So think about if you're drawing a triangle if your perpendicular bisector intersects a vertex, so when I come back here, if I had drawn this, see how this perpendicular bisector, here's the vertex, it's close to the vertex. Assuming this was moved over, if this was moved over here, and my perpendicular bisector intersected that point, what do you think it tells us about this triangle? No, because that didn't happen here, right? None of these intersected a corner. That one didn't, that one didn't, that one didn't. So let me show you a better picture of what I'm talking about, when it actually happens. So if I have a perpendicular bisector, hold on, let me. If I have a triangle, the bottom of my triangle is 5, let's say 5.6. So what's half of 5.6? Let's see, that's going to be 5.3 or 2.5, 6, 7, yeah, 2.8. Right there. If I do my perpendicular bisector straight up from this, and it goes right through that vertex, what do you think that tells us?
Both the other sides.
Yeah, these two sides have to be the same, so what does it tell us about the whole triangle?
Isosceles.
It's isosceles. The whole triangle is going to have two sides that are exactly the same. And we can also prove that the two triangles are the same before I added those tick marks for another reason, because we could say if these two sides are the same, and I have a 90-degree angle here, which means I have a 90-degree angle here, and this reflexive side that goes through this vertex is the same, then by side, angle, side, this triangle has to be the same as this triangle. By side, angle, side. Okay? So, if a perpendicular bisector intersects a vertex, it means it is an, not equilateral, but isosceles triangle. Okay? It will also happen in an equilateral triangle, because an equilateral triangle is an isosceles triangle. But in an equilateral triangle, it'll happen from every side. If I took this triangle and I did the same thing with this side, that one's going to not hit perfectly here because these two sides aren't the same, right? So it only guarantees you, if you only do one side and so you only see it goes through one vertex, then you only have guaranteed yourself an isosceles. You'd have to do at least one more side to see if it also went through that second vertex to see if you were equilateral. Okay? Tomorrow we're going to have an activity that we're going to do in Schoology, so make sure you bring your device. You'll always do every day anyways, you're good. And today's assessment is also in Schoology.